In this video, I'm going to be going through Lewis structures, Vesper, which is molecular geometry, and polarity of molecules. So just to give a brief introduction, when I talk about Lewis structure, I'm talking about Lewis structures of molecules. Now, a molecule is a covalently bonded group of atoms. That's the key. NaCl is not a molecule. H2O is a molecule. How can we tell if something's going to be covalently bonded? You look for generally nonmetal bonded to nonmetal. So we're not going to do Lewis structures of ionic compounds. These are always going to be covalent molecules. Vesper stands for valence shell electron pair repulsion. So Vesper theory is basically the idea that the electrons are always going to repel each other as much as they can. So they're going to form these kind of three-dimensional shapes that maximize the repulsion around them. Polarity of molecules indicates whether a molecule will be polar or not. And what does polar mean? Polar means a molecule has like a positive end and a negative end. You guys probably all know that water is polar. That's because in a water molecule, the oxygen is slightly negatively charged, and the hydrogens are slightly positively charged. So we're going to be able to look at the Lewis structures of molecules and based on just the geometry, tell whether they're polar or not. So let's start with Lewis structures. So I have the basic rules for how to do Lewis structures. I'll explain it now. It might not make that much sense just in text form, but we'll go through with some examples and you'll understand it. So the first thing you're going to do is make a skeleton structure, which is all single bonds. So lone element is always going to be the center. Carbon is the center as well. So basically, you look for which elements by itself, you're going to put that in the middle. If you have more than one choice, generally carbon is going to be in the middle. For example, the first one we'll do is carbon tetrachloride, Ccl4. So if we have Ccl4 as our formula, the basic skeleton structure is going to look like this. Carbon in the middle, and then we're going to do 1, 2, 3, 4 chlorines around it, like this. Okay? Now, if you have 2 branches sticking off, you generally just go left and right. If you have 3, you generally go left, right, and up. And if you have 4, it goes around in this type of pattern. So that's just called a skeleton structure. It's bare bones. We're going to be adding stuff onto it. And these dashes represent single bonds, which are 2 electrons being shared. The next thing we're going to do is add lone pairs to every atom until they all have 8 electrons. Dashed lines count as 2 electrons for each atom. So basically we need to make it so that all of these atoms all have 8 valence electrons. So let's start with this chlorine here. It has 2 from this dash, and we're going to need to get to 8. So we're going to add 6 more like that. This one, same thing. 2, 4, 6, 8. Like this. Like that. Okay? Now let's look at this carbon in the middle. This one has 4 single bonds attached to it, so it already has 8. Now you might say, hold on, that's like not fair because you counted these 2 electrons as belonging to the chlorine. So how can these same 2 electrons also belong to the carbon? That's just the way it works. They're both sharing those electrons, so they both are experiencing the electrons. So this carbon in the middle is done. It has 2, 4, 6, 8 already. Okay? Next, count how many valence electrons are in the formula. So Ccl4. We're going to count how many valence electrons. So for this, you need to know, you have your periodic table. You need to know the groups. Basically, your groups go 1A, 2A. You skip all those transition metals. You start at group 13, and you call it 3A, 4A, 5A, 6A, 7A, 8A. And that number tells you how many valence electrons. So carbon is in group 4A, which means it has 4 valence electrons. Chlorine is in group 7A. It's a halogen, 7 valence electrons. But because there's 4 chlorines, 7 times 4 is 28. So this is a total of 32 electrons. So basically, when these elements come together, they have 32 electrons, valence electrons, that they're going to distribute. Step 4. Count how many total electrons are in your Lewis structure. So let's look back at our Lewis structure, which we drew here. Let's count the electrons. The dots count as 1 each, so a pair of dots is 2. The dashed line is a single bond with 2 electrons, so that counts as 2 as well. So starting here, doesn't matter where you start, but 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So we had 32 before, we have 32 again. If these numbers match, you're done. If they don't, just be a comma here. If they don't, turn single bonds into double or triple bonds until the numbers do match. So in this case, we have 32 and 32. We're done. So therefore, this is in fact the correct Lewis structure for CCl4. But if they don't match, we're going to have to add turn single bonds into double or triple bonds. And we'll go over some examples of how we do that. Now this relates directly to Vesper as well. So instead of just practicing more Lewis structures, let's go right into Vesper with this molecule. So as we showed before, the CCl4 molecule is going to look like this. One carbon in the middle of 4 chlorines with lone pairs around the chlorines like this. And what Vesper means, the valence shell electron pair repulsion, means that these chlorines are going to want to be as far away from each other as possible because electrons want to repel each other. So think about what shape they're going to have in order to completely be as far apart as possible from one another. You're probably thinking a cross shape, like this. But if that's what you're thinking, you're not thinking three-dimensionally. If you give them 3 dimensions to work in, there's actually a better way that they can rearrange, and it's called the tetrahedral shape. And it kind of looks like this. Okay, it kind of looks like, as best I can display that, sort of like a little tripod with one sticking out of the top. This shape is actually a better geometry because these are farther apart than they would be if they were a cross shape. So this is the actual 3-dimensional shape that this molecule is going to take. We call this shape tetrahedral. Let's write that down. Tetrahedral. Okay, it's the geometry when you have one central atom and 4 branches coming off of it. Tetrahedral shape. Okay? Now, let's jump right into polarity. Let's just go like one example at a time with everything. When it comes to polarity of a molecule, whether a molecule is polar or not, you might think it has to do with maybe the electronegativity difference between these, which you may have gotten to before this video or not. Basically, electronegativity is how well there's a pull for electrons. Highest electronegativity means it's going to pull really hard on shared electrons. Lower electronegativity means it can't quite pull as hard on shared electrons. And I happen to have some of these numbers memorized. Chlorine has an electronegativity value of 3.0. Might be 3.5. Can't remember. But it's at least 3. Carbon is lower, 2.5. So there's a big difference in electronegativity here, which means this chlorine is technically hogging electrons from this carbon. Same as all 4 of these. They're all kind of pulling the electrons away from the carbon more. So you might expect this to be a polar molecule because of that. But because they're all pulling in perfectly opposite directions, it's canceling out the polarity. It's pulling in perfectly opposite directions, so it becomes a non-polar molecule. So basically when it comes to polarity, a symmetrical molecule is going to be non-polar. And by symmetrical, you got to really think about it 3-dimensionally, and you really want to picture like where the pull of the electrons is. A good way to think of it is this. Imagine this molecule is like 4 kids on a playground all trying to pull this ball away. And this ball has like 4 chains on it. So each kid grabs a chain and they're all trying to pull with the exact same strength. Well, because this is, now my model might not be perfect tetrahedral, but because in theory it's perfectly spaced apart, that ball in the middle is not going to go anywhere. And that tells you that it's going to be a symmetrical molecule. So this molecule is going to be nonpolar because the polarity kind of cancels out. Now we could make this more complicated. I could say, well, what if instead of CCl4 it was CCl3F, or instead of this being a chlorine, I can swap it out and make this a fluorine. Well, that just changed it up. It's kind of up to your teacher if you're going to get examples like that at your level. Okay, but basically if all 4 of these branches are the same element, they're all going to be pulling with the exact same strength, and you're going to get a non-polar molecule. Let's do another example. Let's look at CO2, carbon dioxide. So let's start with our skeleton structure. Now carbon's the one that's by itself, so that's going to be in the middle. We're going to put the 2 O's like this, and that's our skeleton structure, COO, like that. Okay, now we give lone pairs to all of these elements until they all get to 8. Now be careful, don't forget the carbon in the middle. This carbon has 2, 4, so it needs 4 more electrons like this. Okay, so this might be the correct Lewis structure, or it might not be the correct Lewis structure. Let's figure it out. So what we do is we count how many electrons are in this. Well, carbon is 4, oxygen is 6, but there's 2 of them, so 6 and 6 is 12. Gives us a total of 16 valence electrons. If this number adds up to 16, then we're good. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I like to write equals 20. All right, we have too many electrons. So what we have to do is turn single bonds into double or triple bonds until we get down to 16. Now to do that, you pick any 2 adjacent atoms, meaning they're neighboring atoms. Now we can do either these 2 or these 2. You remove a lone pair from each of them. So let's say I want to make a double bond right here. I'm going to remove these 2 and these 2, not just those, both. You remove from both of them and then you make the double bond. Okay? Now this should cut us down by 2. 2, 4, 6, 8, 10, 12, 14, 16, 18. Because this now counts as 4. So now we're down to 18. We're down to 18. 18. Okay? We're close, but we're not there yet. Now, you could probably guess we can just do the same thing on the other side and remove another 2 to get down to 16. Or in theory, we can remove these electrons and get a triple bond. But what you want to think about is a single bond, triple bond, is that very balanced? No. It's going to be much more stable when it's double bond, double bond. It's like if you're at the gym and you're lifting weights. If you want to lift 100 pounds, you're not going to lift 25 pounds on one side and 75 on the other. No, it's going to be balanced out. So what we do here is we take these 2 and these 2 away, make a double bond, and this is going to be our Lewis structure. Let's just check. 2, 4, 6, 8, 10, 12, 14, 16. 16. Okay, if we want to rewrite it a little neater, we write the carbon in the middle, double bonded O, and now each of these O's has 2 lone pairs on it. 2 lone pairs, 2 lone pairs. And the best way to represent this is to kind of think in terms of repulsion. Those electrons are kind of be angled on the sides like this. Okay, so that's kind of the best way to represent it. We can fix that a little bit. Okay, so that's the Lewis structure of CO2. Now, let's think 3-dimensionally what this really looks like. Okay, let me grab my clay to kind of demonstrate this. So if I want to represent this red one in the middle as my carbon, and I could have these 2 pencils as my double bond. Same here. The question we have to think or ask is this in fact going to be the correct 3-dimensional shape? I mean, I just copied what I have on the board here. Is this a correct shape? And yes, it is, because this oxygen is going to repel this oxygen as much as it can. And if you think 3-dimensionally, what's the best way for these to repel? It's to be straight across. So notice the 3 elements now form a straight line, so we call this linear. Linear. Basically, when you have 2 branches and no lone pairs in the middle, which we'll get to in a sec, it's going to be a straight line, straight across, and we call that linear. Now in terms of polarity, the CO bond is very much a polar bond. The O is extremely strong. I know O is 3.5, and I know carbon is 2.5, which makes the CO very much a polar bond. But because they're pulling in complete opposite directions, it's perfectly symmetrical. It cancels out, so therefore this is going to be a non-polar molecule because it cancels out. Okay? And again, imagine these are like 2 kids on the playground trying to pull at this ball in the middle. They're pulling with the same strength in opposite directions. It's not going to go anywhere. That tells you that the polarity is perfectly symmetrical. Okay? Let's do this example here with HCN. All right. Now, we have 3 lone elements, meaning nothing's doubled up, so we can pick. But generally, when you have a choice, carbon's going to be in the middle. Carbon makes a good central atom because it has 4 valence electrons, which means it really has 4 areas for other elements to latch onto it. So we're going to put the 2 elements on the sides, and we're going to write the H here and the N here. You could, in theory, switch them, but I mean it's written as HCN, so we're going to write HCN. Okay, that's the basic skeleton structure. Now we're going to add our lone pairs. So the nitrogen needs these, the carbon needs these. And I should have mentioned this sooner, but hydrogen is done. It only ever wants 2 electrons. It can't hold 8 electrons. It only ever wants 2, and that's because it's, located at the very top of the periodic table, very close to helium in terms of atomic number. So it can only ever hold 2 electrons. So you're never going to put dots around a hydrogen. So this is in fact correct for the skeleton structure. Okay, let's find out if this is correct. So H is 1, C is 4, N is 5. 1 plus 4 plus 5 is 10. 2, 4, 6, 8, 10, 12, 14. Okay, so the first thing we have to do is turn one of these into a double bond. Now, this cannot form a double bond. Why? Because the hydrogen doesn't have any extra electrons that we can erase, right? And also, hydrogen can only ever hold 2 electrons max, so it can't possibly share 4 electrons. So the double bond's going to have to be on this side. So let's remove this, and let's turn this into a double bond. This should have cut us down by 2. Let's check. 2, 4, 6, 8, 10, 12. We're still not done yet because we have 10 and 12. So obviously we're going to take another 2 away and we're going to form a triple bond. Triple bond. 2, 4, 6, 8, 10. This is correct. Now in terms of the geometry here, we have a hydrogen sticking out of one side and a nitrogen sticking out of the other side. So we can kind of represent this sort of like this. Now, it's not perfect because I only have 2 colors here, but we can assume that this is the N and this is the H. Now, what shape is that going to be? Linear, just like the one above, because it's 2 branches sticking straight out, so it's going to be a linear shape. Linear. And let's think about the polarity. Well, they are pulling in perfectly opposite directions, but the thing is, because this and this have different strengths, specifically different electronegativities, it's no longer going to be symmetrical. Geometrically, yes, it's symmetrical, but if you think about the pull of the electrons, the electronegativities, it's not symmetrical because the N is going to be much stronger than the H. So because it's not an even pull in opposite directions, this is going to actually be a polar molecule. So we have nonpolar because these are exactly the same, pulling in perfectly opposite directions with perfectly the same strength. This, even though it's linear, it's polar because this one is pulling stronger than this one. And again, how do I know that? I just have certain electronegativities memorized. You'll be given, if you haven't already, an electronegativities chart, so you can look up the N, which is 3.0, and the H, which is 2.1, and you can realize that they're different and pulling with different strengths. All right, next let's do NO2 minus, which is nitrite. So we can actually do polyatomic ions that are covalently bonded. Now I know you're saying, wait, ionic and covalent? Well, this is an ion, but the NO2 itself is held together through covalent bonds. So we can do a Lewis structure for the NO2. So N goes in the middle, O, O, like this. Dots, dots, dots. Okay, let's see if this is correct. N is 5. O2 is 6 and 6, which is 12. That's 17. But notice there's a minus here. It's an ion. So how do you end up with a minus? Well, you must have had 1 more electron than you're supposed to, or at least, 1 more than you would expect here. So because the minus tells us there's 1 extra electron, let's count that as 1. So this ends up being 17, 18. 18 electrons. Okay? And again, if it were just NO2 with nothing else, that would be 17 electrons. But because there's a minus here, it tells us that there's an extra electron in there. All right, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20. All right, hopefully by now you see what we're going to have to do. Erase 2 and 2 and give it a double bond. Now, I chose to do it on this side. You can just as easily choose to do it on the other side, completely fine. In fact, some teachers might ask that you show it both ways, and those are called resonance structures. Ask your teacher if that's required. So here I just happen to choose the right side, and this is going to be my correct Lewis structure. But because this is an ion, we have to write the charges, and what we do is we put the entire molecule in brackets, and we put the charge outside like that. So this is NO2 minus nitrite. Okay? Now let's think about what the shape of this is going to be. Let's look at our central atom here. The nitrogen has two branches sticking off. So based on what you see here, you would think this is going to be linear. Okay? Straight line. But the thing is, the presence of this lone pair throws that off. An important concept here is that a single bond, or a double bond, or a triple bond, or a lone pair are all going to repel each other equally. You might think, well, wouldn't the double bond be twice as strong as a single bond and push it farther away? No. It's actually going to repel exactly the same. So if you think about it, this nitrogen has kind of three regions of electrons around it. 1, 2, 3. Those are going to arrange themselves in this triangle shape, but because the lone pair isn't a real bond, it's just two electrons, it doesn't actually show up in the geometry. Here's what I'm getting at. Okay, so this red one will be my central nitrogen. We're going to have a single bonded oxygen sticking off one side. We're going to have a double bonded oxygen sticking off another side. And we're going to have a lone pair, which I'll represent by this third pencil, coming off of this. Okay? So, 1, 2, 3 bonding regions, or I should say 3 electron regions around that central nitrogen. So this is what it would look like, and this shape would be called Trigonal Planar, and we'll get to that later. It's a triangle on a flat plane. But again, because you don't actually see these electrons, we take that off, and this is a shape we have. We call this shape bent. It's a bent shape, bent. That probably resembles water, right? And we're going to see water looks the same way. Now, another way to kind of visualize this is this. If this lone pair weren't there, what would this look like? Well, it would look straight across like this, right? It would look kind of like a CO2, just straight across like that. But this isn't the only thing in play. There's also this lone pair here. So what's the result? Well, the lone pair is going to skew these two legs down like that. So this is what we end up seeing. Okay? Once again, if it were no lone pair there, it would be straight across. But because there's a lone pair, it skews those two legs down. So now we have a lone pair up here where my finger is, and then a branch like that. So this is called bent. Now, in terms of polarity, all bent molecules are going to be nonpolar. Polar. All bent molecules are going to be polar because this can no longer be symmetrical. If it were straight across like this, it would be perfectly symmetrical and it would be nonpolar. But because they're now bent, it throws off the symmetry. It's pulling now in different directions. So therefore, it's going to be a polar molecule. Polar molecule. All bent structures are always going to be polar. All right, let's do H2O, classic water. O in the middle, H on each side, dots around that. Now remember, H doesn't get any extra dots. It's fine with its 2. So this might be correct, it might not be. Let's see. So H is 1, so 2 H's is 2, plus 1 oxygen, which is 6, so that's 8. 2, 4, 6, 8. So this is correct. This is, in fact, the correct Lewis structure for water. So what shape is this going to be? Well, you'd probably look at that and say linear, straight line. But you all know that water is shaped differently. We've been drawing water molecules like this all year. Or you've probably seen, like something like this representing water. So let's talk about why it's bent like that and not straight across. Imagine you're just looking at that central oxygen. Just looking at that central oxygen. What does it have on it? How many regions of electrons? Well, 1, 2 bonds and 2 lone pairs. So really there's 4 electron regions. When you have 4 electron regions, those are going to push themselves away with equal strength. You're going to end up with this tetrahedral shape. Did I lose a pencil somewhere? You're going to end up with this tetrahedral shape as your water molecule, or at least as a central atom. Tetrahedral shape as your central atom. But because you don't actually see these electrons in real life, they don't stick out like this. When we take them away, you can see what the actual shape is. And there's your bent water molecule. Okay? Another way to think of it is, this would be straight across like that. If that were the only thing in play, this would look like a CO2 now. This would be the only factors at play, these 2 bonds. But because you have those other 2 pairs here sticking in like that, those 2 pairs are now going to skew these 2 branches down, and this is what we end up seeing. Just that bent water molecule. Okay, so to sum up bent, because these are both considered bent, but you'll notice they're a little bit different. Bent. Anytime you have a central atom with two branches coming off, it's either going to be linear or bent. It's linear if the central atom doesn't have any lone pairs. For example, CO2 looks like this. Notice central atom, two branches, no lone pairs. HCN, central atom, two branches, no lone pairs. These are both going to be linear. Anytime the central atom has one or two lone pairs, it's going to be bent. So this nitrogen has two branches coming off, but because it has a lone pair, that's going to skew those branches down, bent. This one here, two branches sticking off the ends, but because it has the two lone pairs, bent. And just like up here, a bent molecule is always going to be polar because the symmetry is thrown off. So all bent are going to be polar. Linear, it's going to be nonpolar if they're the same thing sticking off like this, or it's going to be polar if they're not the same thing. And just to review, tetrahedral, always going to be nonpolar if it's the same four elements. You could throw a curveball in there and say, well, what if one of these was like a fluorine? Well, that just changes it. And that's up to your teacher to see how deep we're going to go with this. Okay, next shape. Let's do So3, sulfur trioxide, not to be confused with sulfate. Sulfate would be SO3 2 minus. Let's just do SO3. S in the middle, 1, 2, 3. All right, dots around the O's, dots around the O's, dots around the O's, and don't forget, right there. People often forget that. Okay, so this might be correct, it might not be. Sulfur is 6 valence electrons. Oxygen is also 6 valence electrons, and since there's 3 of them, that's 18. Gives us a total of 24. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay, so hopefully by now you realize what we have to do. We're going to have to make one of these single bonds into a double bond, which will bring us to 24. Now we can choose whichever one we want because technically these are all adjacent with the sulfur. So that's definitely going to go, and then we could pick any one of these. I'll just pick this one because I'm closest, and we give it a double bond. Okay. Again, sometimes your teacher might require you to draw it 3 times with the double bond in different places. Those are called resonance structures. That's up to your teacher. Okay, so now let's look at the shape we have. First of all, let's double check. 2, 4, 6. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so this is the correct Lewis structure. Let's think about what we have here. We have a central sulfur in the middle with how many electron regions? 1, 2, 3. Remember, a single bond, double bond, triple bond, or a lone pair all have the same repulsion. So there are 3 regions around here. So what's this really going to look like three-dimensionally? Well, we have a double bonded oxygen. I mean, this is kind of like what we're seeing now, if I just copy what's up there. We see a double bonded O, a single bonded O, and a single bonded O. But is this what it's really going to look like in real life? No. These are going to repel each other, and they're going to form this perfect kind of triangular shape like that. And again, you might think, well, hold on, isn't the double bond twice as strong? So isn't the double bond going to like skew these this way? No. They all push with the same strength. So this is the shape we get. In terms of the name of this, it's a triangle that lies on a flat plane. So we call this Trigonal Planar. Trigonal Planar. It's a triangle that lies on a flat plane. Let's talk about the polarity of this. 1 S in the middle of 3 O's. Imagine these 3 O's are 3 kids on the playground pulling at that ball in the middle. Is that ball going to move? No. It's perfectly symmetrical because it's pulling in completely opposite directions. So therefore, this is going to be a non-polar molecule because it cancels out. And again, you might say, well, hold on, isn't the double bond going to be twice as strong as the other? So isn't it kind of going to pull it more this way? No, they all pull with equal strength, so this is going to be non-polar. Good overall rule, when it's trigonal planar, if it's 3 branches, if they're all the same element, it's going to be non-polar. And again, we can throw a curveball here. I can say it's like 2 of these are O's and 1 of them's like a selenium. Yeah, that would throw it off. But generally, if they're all the same, it's going to be nonpolar. Let's do one more. NCl3, nitrogen trichloride. I'll do it here. So, nitrogen in the middle. When we have 3, we go left, right, and up. Cl, Cl, Cl. Dots around like this. Dots around like this. And don't forget the lone pair on the nitrogen. 2, well, I'll count this first. 5 for the nitrogen. Cl is 21. Well, I should say Cl is 7. Times 3 is 21. Gives us a total of 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. What did I do wrong here? Hold on. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 26. There we go. So this was 26 both times. Now, how did I know I messed up? You're never going to get too few. I just had 24 there. If you do that, you mess something up like I did. I counted wrong. Okay, so 26, 26, this is in fact the correct Lewis structure. It's all single bonds with a lone pair right here. So you might think this is going to be the same shape as the last one. 3 branches coming off, so isn't it just going to be a perfectly trigonal planar shape? No, because look what else we have. A lone pair that's going to throw it off. Okay, so again, it's not just going to look like this. It's not just going to be trigonal planar, which looks like this. It's not going to be this. We have that lone pair here, and what's that lone pair going to do? It's going to skew these down like that. And this is a shape we now have. If I can angle that as best I can. The lone pair kind of skews these down. Imagine a lone pair of electrons sitting right here. That's really what we're looking at. But in reality, you don't actually see that. So this is a shape we have. We now have a pyramid shape. But notice the base of the pyramid is a triangle, as opposed to like in Egypt, the pyramids are technically called square pyramids because the base is a square. This is a pyramid with a triangular base, so the geometry is called Trigonal Pyramidal. Or pyramidal, I've heard it both ways. Trigonal Pyramidal or Trigonal Pyramidal. This is the shape we have. Now, if the molecule were trigonal planar, if the molecule were trigonal planar like this, what would the polarity be? Non-polar, because they're pulling in perfectly opposite directions. But notice that when we bend it like this, due to the presence of that lone pair, we are no longer perfectly symmetrical. Imagine these are 3 kids in the playground pulling on this green ball. That green ball is going to move. So therefore, it's not perfectly symmetrical. This is going to be polar. Every time you have a trigonal pyramidal shape, always going to be polar. Can never be nonpolar. Even if in theory these are all the same element, it's still going to be polar. Okay? So let's just sum up the last 2 shapes. What do these 2 have in common? 3 branches coming off them. And by 3 branches, I mean 3 atoms. So 3 atoms coming off the central atom. 3 atoms coming off the central atom. So how are they different? This one has a double bond and 2 single bonds, meaning no lone pairs in the middle. No lone pairs means it's nothing to throw off the symmetry, it's trigonal planar, and it's going to generally be non-polar, unless one of these is different. This one here is different because it has 3 branches and a lone pair. That lone pair throws off the geometry, gives you that trigonal pyramidal shape or pyramidal shape. This is going to be polar. Okay? So, why don't you pause the video and give me Lewis structures, Vesper shapes, and whether the molecule is polar or nonpolar for all 6 of these. All right, so let's start going through them. First, O3. This is called ozone. You've heard of ozone. Well, that's what it is. All right. O3. So we're going to go O, O, O. Obviously, there's no real central atom here. It's just 3 O's. All right, dots all around. Dots all around. I don't know what happened here, but okay. Now, this might be correct, it might not be. O3, that's 6 plus 6 plus 6, which is 18. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20, we have 2 too many, so what do? One of these gets a single bond, or turned into a double bond. Doesn't matter which one you choose. I'm just going to choose this one. And that is now our correct Lewis structure. That brings us down to 18. Let's think of the Vesper shape. If you took a quick look, you might say that's linear. But it's not. Because look, it's in a line, but the lone pair is going to throw it off. So really, this central O has 3 bonding regions, so you can even rewrite this if you want to be more correct like this. And then we could add the lone dots here. Notice the lone pair counts as an electron region, so it's going to push these down in this shape. Now, you don't actually see that in real life sticking out, so we call this shape bent. And all bent molecules are polar. Even though this is 3 O's, meaning there's literally no electronegativity difference between them, it's still considered a polar molecule. Now, if you want to go deep with this, it's not as polar as something like, if this were different elements, but it's still technically polar because of the uneven distribution of electrons. Okay, so again, we have bent and polar. All right, let's do the next one, Pf3 Phosphorus Trifluoride. So, phosphorus in the middle, 3 fluorines around it. Let's add dots. And don't forget the phosphorus. All of these need 8. Okay, let's check. Phosphorus is 5, fluorine is 7, times 3 is 21, 5 plus 21 is 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So we're good. This is in fact the correct Lewis structure. Now what shape is this going to be? Well, we have 3 elements sticking off of it. That tells you it's going to be trigonal. 3 of them. Think triangle 3. But because we have a lone pair there, that lone pair is going to kind of skew it down. So this is going to be that trigonal pyramidal shape. If you want to kind of show what this would look like 3-dimensionally, put your phosphorus here, and the 3 F's kind of go down in kind of a shape like that. And sometimes we even give it like wedges or dashes to show 3 dimensions. But basically these go down in a pyramid, and then we have the lone pair up there. And you could add your dots to there as well. So again, the shape here is called Trigonal Pyramidal. And this is going to be a polar molecule. All trigonal pyramidals, all bents are always polar. Ccl4, silicon tetrafluoride. Si in the middle of 4 F's. Let's add dots. Silicon in the middle doesn't need any dots because it already has 2, 4, 6, 8. Okay. Si, that's 4 electrons, just like carbon. F4 is 7 times 4, which is 28. Total of 32. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So this is, in fact, the correct Lewis structure. Let's think about what the geometry is going to be. Well, we have one central atom surrounded by 4 single bonded atoms. This can only be one thing, tetrahedral. And because they're all the same element, this tetrahedral shape is going to be nonpolar. Even though I know for a fact fluorine is the most electronegative element. It's what I call the 4.0 GPa of the periodic table, meaning it has an electronegativity of 4.0, and I know silicon is less than that. Even though the fluorines are hogging the electrons from the silicon, because they're pulling in completely opposite directions, the molecule itself is still nonpolar. N3 minus, or let me phrase that differently. N3 minus. Okay? This isn't a single nitrogen atom with a charge of 3 minus. It's N3 with a charge of minus. This is a polyatomic ion. I think it's called azide. I used to know. I just pulled up an example. N3 with a charge of minus. All right, let's do this one. So 3 N's are going to look like this. Okay, just 3 N's in a row. Let's give them all their lone pairs. This might be correct, it might not be. So, nitrogen is 5 valence electrons. So this is 15. But because there's a minus here, that tells us there's one extra electron, which means there are 16 valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's 20. So we now have a choice. We can either do 2 double bonds or 1 triple bond. Okay? Now I know nitrogen can certainly do triple bonds. We see it all the time. But in this case, to be more stable, instead of triple and single, it's going to be a double-double. So just to piece together how this goes, we remove 2 electrons from these two, give it a double bond. And then we remove 2 electrons from these two and give that a double bond as well. Okay? So let's think about what this geometry is. We have 2 branches coming off. So this is either going to be linear or bent. Well, look at the central nitrogen. Does this have any lone pairs? No, meaning it's straight across, meaning it's going to be linear. Linear, and because the 2 branches are the exact same element, this is going to be non-polar. Okay? The only way linear is going to be polar is if one of these is different. So this is definitely going to be non-polar. OF2, oxygen difluoride. This one I believe doesn't really exist, but it's a good example for Lewis structures. Oxygen difluoride. Alright, so the O is in the middle. We get the 2 F's on the left and the right. Let's give them all lone pairs. Okay, oxygen is 6, fluorine is 7 times 2 is 14. Gives us a total of 20. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So, this is correct. What's our geometry? Well, again, you might just say linear, right? Even like if you looked at this two-dimensionally, you could say, hey, look how perfectly symmetrical this is right down the middle. It's perfectly mirror image. You're not thinking three-dimensionally. Three-dimensionally, that O has 4 electron regions coming off of it. 2 of them are fluorines, 2 of them are lone pairs. And you might say, well, hold on, you're just kind of like cherry picking here because you put the 2 next to one another. Well, look, wherever I choose to put this second one, it's still going to be bent. Wherever I choose to put this second fluorine, it's still always going to be bent because you don't actually see these. This is all you see. Whenever we have what looks like a linear molecule with 2 branches, anytime there's either 1 or 2 lone pairs, that's going to end up being a bent molecule. And a bent molecule is always always polar. A bent molecule is always polar because even though these are pulling with the same strength, they're no longer pulling in opposite directions. They're pulling in kind of skewed directions. Last one, CO3 2-, that's carbonate. All right, carbon in the middle. I realized I made a mistake on the last one. I'll go back at the end. Carbon in the middle. 3 oxygens around it, like that. Let's count electrons. Well, let's give it lone pairs first. Don't forget the carbon. Okay, let's count how many we have here. So carbon is 4. 3 oxygens is 6, 6, 6, which is 18. But it's a -2 or a 2-. So how do you become 2-? You have 2 extra electrons. So let's call this 2 extra electrons. This gives us a total of 24 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So we have 26. We have 2 too many. So what do we do? One of these becomes a double bond. Doesn't matter which one we choose, but one of them becomes a double bond. Okay, let's look at the shape we have here. Well, let's double check the number first. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. There we go. 24, 24. Now, what shape is this going to have? Well, the central carbon has 3 things coming off of it. That's going to make it trigonal. And because it doesn't have any lone pairs, it just has these 3 branches, that's going to be trigonal planar. They all pull in completely, perfectly opposite directions with perfectly opposite strength, so it's just going to become that triangle shape. Trigonal planar. And don't forget, when we have an ion like this, we need to put the entire thing in brackets and put the charge on the outside. In fact, that's what I said I forgot in the last one. When you have a polyatomic ion, you want to put brackets and you want to put the charge. So I did the N3 minus. I should have put my brackets with my minus out there as well. Okay. In terms of polarity, 3 oxygens pulling in that perfect trigonal planar shape. They're pulling exactly opposite one another. This is going to be nonpolar. Nonpolar. Okay? So just to sum up real quick, let's try to sum up the entire kind of Vesper shape video here. If we have two branches, meaning like a central element with 2 things coming off of it, it can either be one of 2 things. It can either be linear, where it's going to look like this. I'll just choose red here. Linear. Or it's going to be bent. Now, it can either be bent because you have a double bond and a lone pair, or it can be bent because you have 2 single bonds and 2 lone pairs. These are both going to be bent. Okay? 2 branches, either linear or bent. Now, how do we know whether it's linear or bent? It all depends on lone pairs. If it's 2 lone pairs or 1 lone pair on the central atom, it's going to be bent. If there are no lone pairs here, it's going to be linear. Now, there are some exceptions to the rule that they all get 8, but barring an exception, how do we actually get this? Generally, you're either going to have a triple bond on one side or 2 double bonds, barring any exceptions, which there are. Okay, if you have 3 branches, meaning a single central atom with 3 things coming off of it, well, now you have a couple options. Let me come separate this. Central atom with 3 branches. One of them generally will be a double bond, and no lone pair in the middle. This is trigonal planar. Or you can have a central atom with single bond, single bond, single bond. I'm drawing this wrong. I'm trying to represent it 3-dimensionally. Single bond, single bond, single bond, and a lone pair. This is trigonal pyramidal. Okay? So again, if you have 3 branches, meaning a central atom and 3 elements sticking off of it, it's going to be trigonal. If it's a lone pair in there, that skews the geometry, gives it the pyramidal shape. If there is no lone pair, it's going to look like this, trigonal planar. And finally, if you have 4 branches, this is easy. It can only ever be one thing, tetrahedral. So in terms of 3 dimensions, it's going to look sort of something like this. Tetrahedral. Okay. Let's quickly sum up the polarity of these molecules. If it's a tetrahedral shape, as long as they're all the same element sticking off, non-polar, because it perfectly cancels out, it's perfectly symmetrical. Down here, 3 branches. Trigonal pyramidal, always going to be polar because of the lone pair. The lone pair is always going to make it polar, even if these are the same element, polar. Trigonal planar, as long as these elements are the same, or I should say as long as the branches are the same element, that's going to be non-polar. Even though there's a double bond and 2 single bonds, they all pull with the same strength. This is going to be non-polar. In terms of 2 branches, bent, always polar, always. Even if it's literally, we did ozone, which is OOO. Even if it's the exact same element, it's still going to be considered polar. Linear, well, it depends. If the 2 branches are the same element, it's going to be non-polar. If the 2 are different elements, it's generally going to be polar. So that sums up Lewis structures, Vesper, and polarity of molecules.